Hello everyone, my name is Alex Markham. I'm doing my PhD in the research group Neuroinformatics at the University of Vienna. Today, I'll be presenting a joint paper with my advisor, Moritz Grosser-Wentrup, on measurement dependence inducing latent causal models. I'll begin by presenting the problem statement. Then I will formally define metal causal models. After that, I'll introduce a term for graph theory, edge-clique covers, and after that, I will explain how we use these to infer metal causal models. I'll finish by discussing the relevance of these metal causal models and some implications. Our problem is focused on measurement variables, in particular when the dependencies between these measurement variables are all induced by unobserved latent variables. We call this strong causal insufficiency. Examples include psychometric data, questionnaires, surveys. In this problem, our task or goal is to learn the inducing latent causal structure. Our approach, unlike non-causal approaches such as factor analysis or independent components analysis, and also unlike causal approaches to measurement models, which tend to use what's called tetrad constraints, unlike these, our approach does not assume linearity of the functions, or Gaussianity, non-Gaussianity, or any other distribution of the exogenous variables. Instead, we leverage some graph theoretic properties of metal causal models. The result is a non-parametric or distribution-free method for finding the minimal causally sufficient latent graphical model. So instead of saying measurement dependence inducing latent causal model repeatedly, I will just say metal causal model, or MCM for short. A graphical MCM is a DAG given by the triple L, M, and E. L and M are disjoint sets of vertices, while E is a set of directed edges between these vertices, subject to the following constraints. All vertices in M have an in degree of at least 1 and an out degree of 0. All vertices in L have an out degree of at least 1. You can see this in the example DAG below. Notice on the bottom row are 4 measurement variables. They all have at least 1 incoming edge and only incoming edges. While our top row of latent variables all have at least 1 outgoing edge. This captures the idea of strong causal insufficiency because none of the measurement variables are ancestors of another. Instead, all of their dependence is induced by latent causes. In order to explain how we actually learn these, I will first go over some graph theory terminology. So to begin with, we have an undirected graph. This is simply a collection of vertices and undirected edges. You can see an example below. Next, we have a clique. This is a fully connected subgraph, or a set of edges in which, a set of vertices in which none of the edges are missing. So outlined below in blue, you can see a clique, A, B, and C. None of the edges are missing. Another example would be D and D, or C and F. However, if we were to consider A, C, and F, this would not be a clique because there's no edge between A and F. Finally, we have what's called an edge-clique cover. This is a set or collection of cliques whose union contains or covers all edges. So if you look at the 3 cliques below, outlined in blue, green, and red, they each contain 3 different edges. And so together, all 3 of them cover all 9 edges in the graph. Also, notice that in the set, we can't remove any of these cliques. And there's no smaller set of cliques which cover all of the edges. So we call this a minimal edge-clique cover. Now we can present the main result of the paper, which is that metal causal models provide a causal semantics for edge-clique covers. So if we wanted to learn a metal causal model, of course, we don't have access to the latents. We can only look at the measurement variables. So to begin with, we estimate the independence relations among these measurement variables. Now, as I've said, all dependencies between these measurement variables are induced. Therefore, we represent it as an undirected dependency graph. One special property of these measurement variables and the undirected dependency graph, which is given by the strong causal insufficiency, is that the unconditional independencies imply or necessitate all of the conditional ones. So we don't have to do any conditional independence testing. We can just do unconditional independence testing, and then we put an edge between two measurement variables if and only if they're dependent. Now, to actually learn the latent structure, there are many possible sets of causal latent variables that could induce it. So we restrict our search space to a minimal causally sufficient set. To actually find this, the MIN MCM, minimal metal causal model, can be found by using the minimal edge-clique cover over the undirected dependency graph. So now we can look at the example below. Imagine we have 4 measurement variables, M1, M2, M3, and M4. We do our independence testing, and we see only 2 independencies between M1, M4, and M2, M4. Now we construct our corresponding undirected dependency graph. Notice the only missing edges are the 2 between M1, M4, and M2, and M4. Now we find the minimal edge-clique cover. This would be over a clique over M1, M2, M3, and over M3, M4. For these 2 cliques, we posit a latent variable with edges going from the clique to the measurement variables that make up the clique. This is essentially our method. Now, for some discussion, for a given set of measurement variables, the MIN MCM is relevant because it is the simplest causally sufficient latent graphical model, i.e., any true generating structure must be a refinement. In the full paper, you will also find how we define simplest, alternative notions of minimality, some properties, proofs about MIN MCMs, an application to a real data set, and how our work and what I've presented relates to existing work, and you'll find some ideas for extending this to future work. Finally, visit my poster later at the poster session, number 244, or see my paper for more details. You can also visit the documentation website, metal.causal.dev, to see the Python package that we use for the application. You can also email me at alex.markham@causal.dev if you have any further questions or would like to discuss this or use this in your research. Thank you.